Okay, let's get started for this Union 2 analysis. So the objective of this union is to understand why algorithm analysis is important and to be able to use the big O notation. So this big O actually is the order. So remember this O actually is order. So actually n order square, that order. Okay, that's why it's called big O notation. It's because the order of growth, the order of growth. Okay, that's the order of growth. How fast the algorithm will scale up. How fast the algorithm will scale up if your number of elements or something grow up. Okay. So to understand the big O execution time or common operation on Python list and dictionary. So in this union, they use the list and dictionary as examples. And then to understand how implementation of Python data impact algorithm analysis, and to understand how benchmark, how to benchmark a simple program. So the benchmark means that when you do testing and try to find out how fast it is, you need to do benchmark. So this usually is for sorting. Say I have some data to sort. Then you can have 2, 3, 1 or something, 4, 5, 7 to sort it. Okay, and a good benchmark is some sample, real world sample, for you to try a program to see if the algorithm is good or not. For example, like students' score from Washington High School, that can be a benchmark, or something that actually provide authority so that people can verify whether a certain algorithm is good or not. That's called a benchmark. So in this union, we're trying to understand how to analyze a algorithm, and then how it behave for asymptotic behavior when the order grows up, and then how to use a benchmark to test a Python program. Okay, is the objective for this chapter. Then what is algorithm analysis? So basically, algorithm analysis is to compare programs. So it is very common for beginning computer science students to compare their program with one another. You may also have noticed that it is common for computer programs to look very similar. And an interesting question often arises when two programs solve the same problem but look differently. Is one better than the other? So basically, the reason why we try to study the algorithm is we try to understand how good the algorithm is. And then, for example, some companies say like Cadence, they do logic synthesis as a product, right? And Christina's company called Synopsys, they also have the synthesis tool, the DC compiler, something like that. Okay, and then which one is better? You know, when the customer come, they will choose, oh, I like this one or that one. They need to fit some benchmarks, say their design of the electronic devices to test the program and test here. So those benchmark programs are used over here to test, oh, this product is better, so let's choose this product, something like that. So you can use a benchmark, you can use analytical model, and then try to get a result to see, oh, this program A is actually better than program B, and they are doing the same job. So I'm going to spend $2 million on this software instead of buying the other one that actually is slower. So that's the purpose for comparing programs. So first one is we have this sum of n. So basically you can sum up from 1 to n. So you actually have the number I from 1 to n, but not n plus 1, but not including n plus 1. So this one, it will give you the sum of n. And then sum of 10 is 51. And then this program called foo.py, if you study it, it has a full-time flat, BO, whatever. But if you look at the program structure, it's exactly the same as this sum of n. So two programs actually are exactly the same. It's said that the name are different. The names are different in this full pie. So these two are different programs and the same algorithm. So the question we raised earlier as whether a function is better than the other. So basically, these two, the functionality are the same. Okay, but the function sum of n is certainly better than the function full because if you are concerned for readability. So there are some important issue in comparing the algorithm. One is readability, the other one is the efficiency, and also the resource requirement. So resource requirement including space, how much disk space it takes, and also time complexity, how fast it will run, or any special device needed. So those are analysis we need to do for comparing program. In fact, you have probably seen many examples. You probably have seen many examples of this in your introductory programming course. Since one of the goals there is to help you to write programs that are easy to read and easy to understand. And normally, engineers has a tendency to write it easy to understand. So that part is not really hard. So because people usually want to make the variable name more readable, but they do have some engineer who will create weird names and then make sure that nobody can read their program. So actually, there are people who do that. So there are a few tips to how to analyze a program. And actually, in the analysis of algorithm, we have systematic way of trying to compare programs. So in this course, however, we are interested in characterizing the algorithm itself. So not only the program, but also we here actually more emphasize on the solution itself, not really which program. And so the previous two program, the sum of n and foo.py, are considered of the same algorithm. We are study more generic problem, not really to evaluate a certain program. But in fact, this generic study sometimes is also applicable to the specific product. And evaluation of a software is a very important job. You know, if you are in the acquisition position for a certain company. Okay. Next one is to analyze or compare program. The first possible way to do is using empirical comparison. Just do experiments. Okay, so usually this is using the timer to compare which one is faster. So algorithm analysis is concerned of comparing the algorithms based on the amount of computing resource, so how much memory you need and how much time you have. And then from this perspective, the two functions above seem similar, but they both use the same algorithm. So the algorithm is the same for the two functions with our two programs we know so far. At this point, it is important to think about what we really mean by computing resources. So there are two resources we concern. One is memory, the other one is time. Two major resources. The study of algorithm is related. So basically, for time, we can do analytical model, and we can also using measurement of time using benchmark to find out which one is actually better. So it usually is in a number of seconds as a measurement result. So here we have a comparison between Active Code 2 and Active 3D. You can find these in the website. And Active Code 2, that's actually wait. Okay, so Active Code 2. Let's look at the program. Let me see. Okay, right here. Let me pick this one. Okay, right here. And it actually in analysis. Okay, and it actually in Python notation. Right here in Python notation. Oh, not yet, not yet, not on the pure notation yet. So it actually was the algorithm study. So here you have the this one this one called sum of n2, okay, and there is another program called sum of n3. Okay, these two programs. One is activity call 2 and one is activity call 3. Okay, so let me see. So the program we are going to compare is active call 2 and 3. So in my library, I have, let me see, I have this one called a program called sum of n2 and sum of n3. So let's compare the sum of n2 and n3. This one actually is the same as sum of n. Okay, so it's actually sum up all of the I from 1 to n. Okay, and this one actually not really taking the calculating the sum. Actually, it just use the formula to do calculation for summation I, right? So this one is way easier compared to this one. Okay, and because it's actually using mathematical model, not really sum up all the elements. Okay, so these two algorithms, of course, the lower one is actually faster than the upper one. Okay, then what can we do? We actually perform the sum of n2 for 5 times, and each time we perform, this is actually 10 million cycles. So let's run this. So actually 10 by 5, that's 50,000 million instructions, iterations. So let's actually try to run it. So as you can see right here, the top part is fast, it's slower because the top part is using sum of n2 and lower part is sum of n3, and sum of n3 is only an equation calculation, not taking sum for all of the loops. So Eric, are you okay with this?
Yeah.
Okay, so this part actually the mathematical model is faster. Okay, so that one is fine, and actually you have the time similar to my previous run. So the next one, summary for this part. But what code does this benchmark really tell us? Intuitively, we can see that the iterative solutions seem to be doing more work. Yeah, because you have a for loop, right? It actually is slower. Also, the time required for the iterative solution seem to be increased if you have a higher number of n, right? And then the sum of n3 actually doesn't grow because you given a n, you just need to do n times n plus 1 divided by 2. So if you can find such a formula, you should try this. Big sigma notation, you should try this. Try not to actually use the for loop to do solution. Is that okay, Eric? That's why the big sigma is very important in many situations. Okay, so we do need a better way to characterize these algorithms with respect to the execution time. The benchmark technique compute the actual time to execute. It does not really provide us with useful measurement because it's dependent on the particular machine program time of delay, compiler, and programming language. Instead, we would like to have a characterization that is independent of the program or the computer being used. This measure would then be useful for judging the algorithms alone and could be used to compare algorithms across implementations. So that part is okay. And we actually, so for when we compare two algorithms, one thing is, well, we run the time, but this actually, when we run the time, it actually depends on this Python language and also depend on the for loop, and it also depends on the machine I have, right? But there are some other way we can actually do analytical model. For example, like how can we actually count the number of a operation or the number of minus operations, so that actually we know which one has more add or more minus. Is that okay, Eric? Hello, Eric.
Wait, how does overloading have to do with like
So you actually
the
can
big
do
O
like
notation and stuff?
add, right? You override this add function, right? So and then you set a counter. So whenever I have a add function, I increase. I'm sorry.
Yeah, so how?
Python, you don't have it, right?
Okay.
Okay. So what happened is like let's go back to the program. So if I evaluate my program, right? And right here, whenever I run this add operator, then my counter increase. So right here, how many count I need to accomplish? I need to finish how many count? I need to go like I need to go by n, right? That's n addition. And how about this one? This one's one add and one division and one multiply. So if you hide the counting operator, the increase or increment of the count in the overridden function, you actually can calculate, oh, totally my add calculate for how many times. And in addition to that, you also need to, if here you have a and B, you should also do the A and B over there, like return A plus B or something. You know what I'm saying? You should also perform the A function. So actually by doing this, overriding the different counter, multiplier, divisor, or swap function or something, you can actually calculate, not in terms of number of seconds, but in terms of how many plus or how many minus. Is that okay? And then it's also possible that you don't
no,
have the
I have a question. So I don't really get why overloading has to do with the stuff you talked about before, like the big O notation and the efficiency of the program.
Here it's actually related to efficiency of the program.
How is it more efficient to overload the operators before?
No, I just want to know how many plus I use, or how many compare I use.
Oh.
Right? So whenever I have an A plus B, then okay, this one, my I plus one for the counter, for the plus.
Okay.
Then totally at the end, I use the count, right? So I can count, oh, totally I have like, I print the count. So totally I have like 10 million plus in my program. And because your machine right now, you may be running PC, you may be running Mac. Okay? So these two different machines, if I compare this algorithm with another one, actually the measurement time on PC won't happen on the measurement time on Mac. But the number of plus sign in Mac and PC should be the same. Right? If you run the same algorithm, should be the same. So by doing that, I know that, okay, if this guy have like 10 million plus, right? I'm sorry. If this program has a 10 million plus, it will also be 10 million on Mac. And then we could compare the two, not two machines, but two programs, one with 10 million and one with 3 million operator. And so we will know that maybe on Mac, the 3 million will still be faster. So overloading is a improvement of the measurement, how we collect the data. Using the timer, that's one way to do it. The other one is using a counter to count how many operator actually I have used. And in terms of which operator is of interest, that actually depends on the programmer. Like, okay, in my algorithm, I think that the plus sign is the most often used operator. Or you say, oh, my HSS in like indexing will have the most operations. Is that okay? Hello? Is that okay? All right, Ariel, is that okay?
Yes, it's fine.
And Monte Carlo simulation is not using benchmark, but using random number generator to test it. Okay, but these are three different empirical comparison ideas. Okay. So we finished the Monte Carlo. Let's look at analytical model. Okay, now we finished those models are empirical. Basically, ask you to do some experiment. Okay, either you run a program, or they require you to run a program by fake data like using Monte Carlo random numbers, or you use the real data by from benchmark typical one, or you actually count the number of operators like plus sign or compare or switch, those swap, those key elements. So now let's look at how can we analyze the algorithm. So basically we can implement the algorithm completely as the first step. So usually you can use a Python to implement it. So that's why one language that can give you quick implementation is important, because you need to compare the Python in quicksort, and then you can maybe in C, C++ is the real target implementation you have. So implement the algorithm completely actually means that try to characterize your algorithm and then determine the time required for each basic operation, such as plus sign or multiplication. And then identify known quantity that can be used to describe the frequency of execution of the basic operations. And then develop a realistic model. So basically now you try to use a Monte Carlo simulation or benchmark to test that algorithm. Okay, these are four major steps you need to set up to test a algorithm. And then here, next one is analyze a known quantity. So that's actually called model input, and then calculate total running time by multiplying the time with the frequency of the operation. So we measure each of the plus sign, right? And then we actually knowing that they are totally 10 million plus sign, and we actually can know, oh, totally is like, if this is 5 nanosecond, it should be 10 million times 5 nano. Okay, so it usually is 0.005. Something like that. That's the way we decide the time for a using analytical model. Okay, the next one is talking about time complexity. So we can measure time really used. We can actually also calculate how many plus sign, and we can also feed the empirical data like random number into there. But here we talk about pure mathematical model. It's like by starting the algorithm, then how many how is the complexity of the algorithm? So basically, if we look at the algorithm itself, the program itself in Python, if we look at a program in Python, okay, let's go back to this sum of. So this one actually, you have a run loop n time, right? And each one you have a equal sign and this one called plus sign. So actually you have like n times the plus sign time plus n times the equal sign assignments time. And maybe this one is like 5C, 5 basic constant unit. And this one maybe like 4C. So totally you end up like n times 9c or 9 and or you parenthesize it, energy it actually is n 9 time constant times c. So eventually this one actually will go to order of n in order of magnitude asymptotic behavior. Okay, so that's the way we build up a mathematical model for analysis there. So we denote that this function by t. T is actually the time complexity, and then it actually is like 1 plus n. And then n is often referred to the size of a problem, and we can read Tn is the time it takes to solve a problem of size n, namely 1 plus n steps. Okay, so that's the way we analyze the time complexity. And then this Tn will be a function, like what I say. At the end, we end up with 9c of n. And then we want to study its asymptotic behavior. So this one actually is order of n. Okay, whatever constant will be ignored, because when it grows, it actually grows in the number order of the n. So the order of magnitude of the function is part of Tn function, and then we try to get the big O notation for order of the function f function. So actually, the number of steps like plus sign or minus sign give us t of n, and then you can use the asymptotic behavior of t of n to get the real big O notation for order of growth. Okay, for order of growth. The next one. So big O notation is asymptotic behavior. And to deal with the asymptotic behavior, it would be if you have order of 1, order of n, order of n squared, order of n cubed, and then exponential n. These different orders, if you have order of 2, you ignore of the order of 1 function. So you have a t n equals 3 x n squared. I'm sorry, n squared plus 2n plus 1. So in this case, we just ignore of those lower order ones. Just keep the most significant one. Okay, that's give you the asymptotic behavior. So and then the constant before it also been ignored. So it will be order of n squared. Okay, so that's actually asymptotic behavior. So we actually end up with this 5n squared plus 27n plus 1005, and 1005 is a constant, so we ignore it. And then second terms, first order, and second order, we'll choose the second order one. So however, when n get bigger, n squared become more important. So actually we summarize it as order of n squared for asymptotic behavior. We don't care about the coefficient before it. We don't care about the lower order number if it is really big. We just care about the orders. So this one is big O notation. And next one, when we study whatever calculator the step T of n, we will have best case, worst case, and the average case. And usually these two are more important because best case usually are ignored. Worst case and will actually kill you if you have a low latency problem, such as like the user or the customer will be fury if actually your worst case performance is too bad, and then you will let the users or customer to wait in the long line. So that's not good. So that's what we describe as worst case. So usually worst case is very essential, and average case is also very essential. But the best case usually is ignored because best case is not a bottleneck for the program. We try to optimize the bottleneck. And the next one, continue the discussion for best case, average case, and worst case. So here we have different level of order of magnitude from 1 and log n, and then n, and then n log n, and then n squared, n cubed, and 2 to the power n. So any question on these? Okay, the next one is the order of growth in plotting. So basically you have the name for the logarithmic growth. And then first order is x equals n, t of n equals n. So you have t of n equals some a n plus something. So the order of n is actually n, that's actually linear. And then here quadratic will be n squared, n cubed, and n of higher orders. I'm sorry, here it's exponential n. Okay. Next one, we'll talk about case study. We will give you a case to study how to analyze the complexity. So here we have a listing. And right here, we have 3 assignments. So totally 3 operators, actually 3 operator here. And then we have a nested loop. So you have n here. So totally right here, it should be 3 times multiply times n squared. And then also 3 times equal sign times n squared. Okay, so totally this part would have 3 the operation time for star plus assignment time times n squared. Okay, and this part would have it should have like n times the plus time, and then plus 2n for the multiply time, and then 2n for the equal time, assignment time, and then last one has 1 assignment time. But this model actually will involve the multiply, equal, and the plus, 3 different operators. And after that, actually, we can model it, and then for first turn, it will be 3, and the second one is 3n squared. So second turn, this turn actually is not completely equal to the first turn 3. The first turn 3 only have equal. And second turn here, you have equal and the multiply. And the third turn, you have multiply and equals and some plus in the third turn. But basically, it got simplified to 3n squared, 3n squared, and 2n, and last one has a constant 1. So this got formulated as the next page. It actually formulated as this. Okay, but if you want to analyze in more detail, it actually is has the equal sign or multiply sign for different time complexity. But let's assume that right here, we actually only have talk about the big O notation, the asymptotic behavior. So actually, you had the n squared term. This one actually is a typo. So let me correct it right on site. Okay, this one is a typo. So this one actually, let me delete this part. So it actually has an n squared term. So this one actually is a order of n squared. Okay, so for asymptotic behavior, actually it doesn't care about the different operators. It doesn't care about the different operators. Also actually, we just want to analyze its complexity. So basically, this one we have the equation of the 3n squared plus 2n plus 4 right? Plus 2n plus 4. And then actually, right here, all of these are minor term. It actually, if when n go enough, this will be dropped. And then any constant or coefficient that will be dropped. So finally, you just need to have the order of n squared. So actually, that is when you analyze the big O notation, it's something like this. And big O notation, actually, you need to come from the T of n first. T of n is time-based complexity. So you analyze to this one, that's called T of n. Okay, that's the time complexity. So how many steps that you take to finish your job? And then you basically take a asymptotic behavior for T of n, you get order of n squared. Okay, you get order of n squared. So the T of n is called the time complexity for the algorithm. Okay, but this actually only talking about the asymptotic behavior. Now let's look at the anagram detection example. So what is an anagram? A quick example of an anagram showing an algorithm with different order of magnitude in a class anagram detection problem for string. So one string is an anagram. If the second is simply a rearrangement of the first one. So heart and earth are anagrams. Heart and earth are anagrams. Heart and earth are anagrams. Okay, Python and Typhoon are anagrams. Pythons and Typhoon are anagrams. So here we have a word listen, and the word listen actually can be rearranged as silence, silent. Okay, you can be arranged as silent. So solution one, let's checking off. Our first solution to anagram problem will check to see that each character in the first string actually occur in the second. If possible, then check off each character. So basically, you have a whole list. Say if my word is HEART, so if you find it in the second list, then you actually check it out, until if everything the second one already consumed, and if everything is checked off, then it actually has the proof for anagram. If not, if there is something left, or when you finish something still in the first one, then it's not a anagram. So basically, that's the first algorithm we will use. So let's look at the anagram number one. So the anagram number one is like this. You basically make the second one as an A list. Okay, and then basically you try to use the position one as zero as a position one, and then you basically try to check off each of the list. So basically, you go through here, and then you try to check if the S1 has something equal to the second one. If true, then you turn found to be true. Originally, try to set it as false. But if you cannot find it, then you continue to increase the position too, so that you continue to check the second list. So basically, this is second list. And if we use the A list because A list is it's actually destructive, and we make the S2 the same one. We don't want to say the second one is Earth, right? So we don't want to destroy it. So actually, we make a list by the second one, so we have a separate one on the A list. But whenever we have this one hard to compare with this, we try to check whether some of the hard H is in there or not. If true, then we found it. If we found it, then we will set the list of that one to be basically to just remove it. Okay, And then if at the end nothing is removed, or actually your first one has not all been checked, then it will not be a anagram situation. Okay, so basically you try to consume the second one, and then you try to check whether everything in the second one it has a match in first one or not. And if it is a match, then we check it out, make sure that actually that one has been taken care of. And until everything is taken care of, then we know that this one is an anagram. If there are still something not being checked out, then we will say that is not an anagram. Okay, so right here we have this one, and we have this A, B, C, D, D, C, B, A. That's wrong. Let me see. We have it. Anagram 1. It's wrong. Anagram 1. So you will just get a 2. Okay, but we can try different things. Say here I add some X in there. It actually, let me see. It's the second one. Let me see. That's the first one. Let me add on the second one. First one. Okay. Add an H over here. Okay, I probably not save. So let me save it. Okay, this one is false. But let me try one more time to put the H on the second one. Probably the previous one, actually, I did not actually save all. So here for anagram. Oh, so actually the algorithm is just checking whether the first one is contained by second one. So the algorithm is only checking for whether the first one is contained by second one. So that's the anagram. So it's checking out everyone in the first list whether it's all contained by second one. So Ari, are you okay with this one?
Yeah.
Yeah. So this one, this is the first solution. Okay. So basically, it just get everyone from this S1. So every time you change the position 1, and then get a string to see whether the second one has that. If found, then we say that one is checked out. Okay. And then if not found, and we will say no, we do not find anything from the second one. So basically that is not an anagram. So basically, if it is an anagram, so the first one's all characters as a set need to be contained by second one. Okay, so the second one need to be it should be a bigger set than the first one. But we do it one by one to check whether it's contained or not. Now let's go second solution. This is the code, so we finished that. So here, actually, I'm sorry, let's go back to this first one. Is the analysis for the order of the calculation of the complexity. So it actually is a CN pick 2 situation. CN pick 2 situation. Okay, so basically let's look at how this come up with as a CN pick 2. So let's go back to the algorithm. So right here, this one should run order of n times in order to make sure it actually goes through it. So here it's try to match all of the members. So basically, you say you have an A, B, C, D, E, and you have A, B, C, D, E. So you basically try to match the number. So you don't need to go through the whole array, but you can do this to check whether it has a match or not. Okay, just partial, just the mutual relationship is good enough. So basically, to analyze the algorithm, we need to know that each of the n character in S1 will cause an iteration to run through the n in the list. So each n position will be visited once. Okay, so the number of the visit becomes the sum of the from 1 to n. So basically each one will, so the first one you visit 1, and then second one you visit, totally you will visit 1 to n. Okay, so that's the compressed, how you come out with this compressivity. How you come out? So the total number of visits is like 1 to n. So basically you have like n in the second list, and then first one you have n element, right? So the first one you go and maybe check out 1, right? And then it will become n minus 1, and then keep dropping because you keep checking that out, right? Until the last one you only have 1. So actually it's dropping like n minus 1, n minus 2, n minus 3 to n to 1. So totally this sum is sum of I, and actually is half of this n times n plus 1 squared. But this one actually, if you analyze it, it actually we drop the non-significant term. So this one actually is T of n, the time complexity. And then the coefficient not important. So at the end, the order is order of n squared. Okay? Hello, Eric, is that okay?
Yeah.
Okay, then sort and compare. That's the first algorithm, is the order of n squared. Second one is the sort and compare. So basically, if we actually, first one, I sort it, right? H-E-A-R-T, you should have a A-E-H-R-T order. And the second one, Earth, it should also have a A-E-H-R-T. So after sorting, you actually compare one by one, whether they are the same or not. This one is easy. So sorting algorithm is the order of n algorithm, and maybe sometimes you can drop down to order of n squared, but you can actually use a merge sort or to drop it to n log n. So it's actually a n log n algorithm by second one, if you have the sorting algorithm. And then the last one, compare, is one by one, just order of n. So you have an order of n log n operator, right? This one actually is n log n. And then the next one, you have the order of n, because this one is comparison, one by one comparison. So eventually, this one is the dominating term. So the compressivity is order of n log n. So this one, n log n is better than order n squared. So basically, you can, by the sorting, if you use the merge sort, it would be order n log n. And if you use the selection sort, it will be n squared. So right here, actually, I have the S1 and S2, right? We actually make the S1 and S2 a new list and sort it. So you won't change the original data. After that, you try to see if one by one it match or not. So you compare one by one, one by one, one by one, if there is a match. Okay, if there is a match. But if there's two are not matched, then we will say it's false. And we will iterate through the S1, the length of S1. But here, of course, the assumption is that S1 is actually the same length with the second one. Or S1 is shorter, then it's fine. Okay. If it's not like that, you have to adjust the length. Is that okay, Eric? Hello?
Yeah.
So that one, this one should be simple. But here we actually present two solutions. So in algorithm study, we try to find out all the solutions. We find out the solutions. We find out all the solutions. Okay, we find out all the solutions. We try to find out all the solutions, and then we will know what is the complexity. And the third one is brute force. Brute force means we try every iteration. This one is stupid approach. So for example, we have this AERHT, right? HRT, right? This heart, right? So we start to do AEH R T A E H T R A E R H T, something like that. You keep iterating. So here you will have M band because it's a whole permutation for this. Is that okay? You list for whole permutation?
Yeah.
Okay. So that's by brute force. And then brute force, actually, we do not provide a solution. It's not hard to generate the full permutation for brute force case. And then this one actually too much because this is actually order of exponential n algorithm is actually n band. N band is a exponential n algorithm. So that one is so-called when it is exponential growth, we call it NP problem. NP problem, non-polynomial time, non-polynomial time. Algorithm. It's a non-polynomial time algorithm. It's an NP problem. Okay, when we see NP, that's actually a non-polynomial time problem. Okay, polynomial time means you have the order of n to the n some number c. C can be 1, 2, 3, 4, 5, whatever. That's called polynomial time. Okay. And about the permutation of Python data, you can actually just find something from internet. That's good enough. So Python algorithm for permutation. Okay, it shouldn't be hard to permute all permutation for a set. Okay, so here actually it's not hard to find to get the whole permutation for a set, something like this. Okay, and you can make it a string after you convert it to when you have got a list. Okay, so that part is not hard. I don't want to discuss that. And then here is the next one is count and compare. So we have permutation. We have the one is so-called sort and compare, and the first one check off 4 different algorithms, and the last one is actually count and compare. Count and compare actually is here it's very rough. So just look at the histogram. So if the histogram is the same, then two are actually the so-called anagram. So let's look at the histogram by pi. Okay, this one is actually histogram by pi. I'm sorry, actually, let's go look at number 4. So number 4 actually is the anagram solution 4. So initially you get a 2 histogram, C1 and C2. C1 to collect string 1's distribution, C2 collect the string 2's distribution, but 0 to 35, that means for all the characters. Okay, so if you got a number, you actually calculate this one so-called order of the letter I. For example, you are B, right? B minus A, actually you will got 1. Okay, so that's your position code, and then you increase the counter for your position code. Same thing, you increase the counter for the position code 2. Okay, same thing, you increase the counter for position 2, and then you actually end up with a collection of the histogram. Okay, and after you have the 2 histogram done, you actually come to here to check whether the 2 histogram are the same or not. Okay, for example, the apple. So apple, you will end up with 1A, 2P, right? And then 1L and 1E. Now this is L, this is 1, and then 1E. Okay, and if both of them have the same histogram, it's the same. But this algorithm is like it actually is you actually will go through what? This one will go through order of n, right? Because you check all the member in one in string 1. This one is also order of n. You check another one, and this one is also order of n. So this one count and compare actually is a order of n. So this one is better than sort and compare. And sort and compare better than Chekhov. And Chekhov better than the brute force, right? This one is order of n. Sorting is n log n, right? Chekhov is n squared. And brute force is n band. Okay, order of n band. Is that okay? Hi, Eric. Is that okay? Hi, Eric.
Yes.
Are you okay with the histogram? You know what histogram is? In statistics, you should have already learned histogram. Are you okay with histogram? Hello?
Yes.
Oh, okay. Then the next one, actually, I have an extra program called histogram. So this one, actually, I have a long sentence, okay? And this long sentence, I converted to lowercase and then clean up the backslash n. And I call something called counter. From collection, there's a function called counter. So two ways to do histogram. Number one is you use your own loop to do histogram. Okay, check every individual character and then increase the counter in the histogram. Second one, you can call a counter, and then it actually will get a histogram in a dictionary. So this histogram in dictionary actually will end up. Let me run it. Let me see. Okay. So when it runs, see here. When it runs, see here. Actually, the dictionary, this letter of histogram, is something that is out of order, right? So after it out of order, I use the sorted the later underlying histogram items, and then convert it back to dictionary and assign to the original histogram. So that one actually put it into order, and then I get the counts and later for value and key, and use that value and key to draw a bar chart. And the bar chart actually have figure and show that actually is the starting of a chart. So this part actually is the one I teach the so-called doing math with Python. And here you actually has a PyLab. You include a PyLab, and in the PyLab actually you can draw the diagram. And this diagram we draw the chart. We show it's actually the bar chart. So bar chart actually we arrange the number of entry using the number of counts. So basically that's the number of count, each one is right here, right? And then we use bar chart and bar X location, which count and align with center. So everything align in the center. And then we use the bar location X and then later to draw out the bar chart and then show grid and data. So by doing this, actually, eventually you got what? You get this chart, that's the histogram. Okay, so the height is the number of occurrence. Okay, that actually is the count. And each of it is like the bar location, and bar location is arranged by number of counts. Okay, and the laters actually, the later is used to draw the symbol over here. So this one X stick is actually the matching the later and the bar location. And bar chart part, so this one, this line draw the bar chart. This line provide an X stick. Is that okay?
Yeah.
And this is the last one, grid, actually provide this one grid. Okay, that one provide grid. So this one is very useful. And then if you need to do histogram and draw something, this one is good. But the one we have, so this one actually called in the library, okay, from PyLab and everything. That's why I told you I give you a book for the doing math with Python to let you learn some of the bar chart, pie chart, and later in the course, in this data structure course, I'll teach you how to draw this different chart. So you save this program, or you can download from my website. And then later, when you have a project, you will be able to print some of these good bar chart in a short time. Okay, that is very useful, even not only for data structure, but also for future course to learn how to use PyLab. Okay, PyLab is very important. It's a very important data field. It's a very important field. Okay, that is a very important field. The next one, this is the program for that one. We see that. Then the next topic is the development of an algorithm. So we compare 4 algorithms, and we know that by an analytical model, we compare the order of n. By analytical model, we compare the order of n, order of n log n. N log n is for merge sort, okay, and normal selection sort, that would be order of n squared. And then the next one for this one is for what? For the checkoff. For checkoff is order n squared. And then brute force is order of n bed. So this one, with the different order, you will find out which one is a beta algorithm by the asymptotic behavior. But now let's look at how to develop an algorithm. So basically, before you develop an algorithm, you should know what type of the algorithm paradigm I'm going to use. Whether I use the brute force, I use recursive, or I want to use the divide and conquer, and then or depth first, or backtracking or greedy algorithm, branch and bounding, and then dimension. These are different paradigms. So recursive is to write a program that actually calls itself somewhere, you know. And brute force, just know whatever knowledge you have, try to get it out. Divide and conquer is like I have a f of 10, I break down to f of 5 and f of 5, something like that. This is called divide and conquer. Or sometimes this is called divide and conquer. And here are different paradigms, you know. The way you figure out, if you don't know what is the answer, but you can think about, I may use one of them to develop an algorithm. So the next one is the algorithm expression. So Python is my algorithmic expression. There are many different ways to express an algorithm, including natural language, pseudocode, flowchart, and programming language. So if you want to express and describe your algorithm, you can use natural language. That means that you use English, right? Second, you use pseudocode. That actually also English-like. And then you draw flowchart, that's okay. But here, actually, I suggest you to use a programming language that is using our Python. So Python is the language I think is good for algorithmic expression. So when you have some idea, you write it as Python and make it work. And later you try to speed it up with C, C++, or put it on a website, you use the JavaScript. Or actually you use the Java to build a bigger website, or PHP for bigger website. So for Python, actually, is a good language right here for us to study the algorithm expression. Okay, that's the purpose why in the summer I would like you to work on this algorithm expression using the Python. And we have the 7 units or chapters in this book. And hopefully this can help you in your data structure course. So program efficiency, 2 things you need to check. One is time complexity, the other one is space complexity. Okay, so time complexity is the order of n, and the space complexity, you can actually check the space complexity. So 2, time complexity you write as T of n, space you may use the S of sub, or memory of order or something, and described by the n. For example, if you use an array, right? Array will be order of n for space, so you actually can write as S of n, right? That's for space. If you will use a tree, okay, that has different complexity, okay, for space complexity. So analyze the program efficiency. You can check the resource, and resource has two types, whether it's time complexity or space complexity. And the next one is running time notation definition. So here you have a constant function. So basically, going up is more faster. Going down is more complicated. Going down is more complicated. So you have constant and then log n, and then n log n square, b to the order n on n band different. And this actually right here, after this is np, non-polynomial time. In cube linear, these are actually these are actually up to here. These are polynomial time. Polynomial time actually also including the one sub-polynomial time because it's actually faster. So it's actually like a set. It's like a set. So if we check the internet for complexity, if you type the polynomial time, yeah, there are several terms. Okay, right here you can see polynomial time. What's a non-polynomial time? Okay, and actually you can say like NP set or something. Non-polynomial. Let me see. Non-polynomial time. Okay, so here is a whole discussion of PMP thing. Your teacher in 6B actually discussed this, right?
Yes, we did like a project on this.
Yeah, so this actually P is polynomial time, right? And inside polynomial time you have constant, right? Yeah. And outside of polynomial time you have NP, and then there's an NP complete, and then there's an NP hard. NP complete means that whatever NP's problem will not be as hard as the toughest one, which is called NP complete. And NP hard is harder than NP. NP is a non-polynomial time, and then polynomial time is right here. So you have NP, right? And then you have NP. NP is non-polynomial time. But non-polynomial time, you have some class called NP complete. Means whatever problem will not in NP set will not be tougher than NP complete. That set is called NP complete. And then there's an NP hard. NP hard means harder than NP complete. Okay, so basically these are the set, and which one actually is the one that you have actually is you need time to study. So that's also another sense that this algorithm study need to take care of. Okay, so to learn algorithm has a few purposes. One is to study the different algorithm, and then the next one is actually to compare them. Okay, so development process that you specify the task and then design a solution, then implement the solution, then analyze the solution and test and debug and maintenance. Okay, so analysis and testing, you basically do time complexity and space complexity, and you need to do worst case, average case, and base case. And which one is more important? For these three cases, which one is more important?
Average.
Actually, worst case is more important. Say I have a internet, right? I need to have a certain.
Oh yeah, true.
So that one you need to meet first, okay? And then the next one is like try to improve the average case. A base case usually don't care about it because well you got a base case, but it doesn't represent everybody, right? So you can study. Oh, okay. The fastest time I can get is how much. But actually, when you design software, usually you need to take care. Okay, worst case cannot be too worse. Okay, an average case need to be acceptable or reach some average, good average. Okay, and then you write after from your algorithm, you write your fully exercise in code, for example, using Python or C++, right? And that actually you actually can do that. And then next one, we talk about data structure. Okay, we talk about algorithm, about time complexity. Now we talk about data structure and talk about the relationship between data structure and algorithm. So now that you have the general idea of big O notation and the difference between two functions, our goal in this section is tell you about big O notation of the operation on Python list and dictionary. So the book and the website's book, it actually use the list and dictionary to discuss the performance of the Python data structure. Okay, so we will show you some time in this element to illustrate the cost and benefit of data. So with different data structure, actually your solution can be different of different algorithmic result. But usually with bigger data structure, you get more storage and then your speed will be faster, usually. But that's sacrificing the space complexity. So here you have a program, and your program have two parts. One is the data structure part, the other one's algorithm part. And data structure part has the ADT, abstract data type. And then data structure has the implementation. Okay, and then ADT, you have domain and function. And then domain, actually it's a data domain. You have the data element organization. Organization means 1D or 2D or linear or nonlinear. Okay, data element is the simple or compound, primitive or compound. Is that the class or is a primitive one? That's called domain. And function is the operation for it. So here is about a class. You have the object and you have the data and the function. Is that okay?
Mm-hmm.
So here maybe ADT is like stack, or you have queue, or you have a list. So right here in Python, we have the list and list dictionary. And function, you have the what? This assessor mutator, get and set, right?
Mm-hmm.
So if we look at this chart, it's something like this. That's the data structure we talk about. And then what's the data structure? There are many definitions available. The data structure is a aggregation of data. Aggregation is like a collection or sum up, okay? Data component that together constitute a meaningful whole. The data structure is a way of arranging data, okay? And the data structure is a collection of data. To me, actually, three sound similar, okay? Okay, whatever. There are several common data structure: array, linked list, queue, stack, binary tree, hash table, graph. So for a CS major, you should be able to implement all of them. All of them. You should be able to implement all of them by your own array, linked list, or your structure or enum. You need to be able to do all of these to implement all of these. Is that okay? So in C double plus data structure 46, this is the minimum work you need to know. 46 class. You need to know, at least need to know how to implement all of that. That's data structure. And then maybe the teacher also covered the algorithm. So that's why we are studying this right here. Okay. And also for those guys who do computing competition in high school, they will also need this. And data structure, we have linear and nonlinear. Linear, we have array, list, queue, stack. Okay, that's one dimension one. And maybe you also have a 2D. And 2D is also, it's not linear, but actually is actually still matrix type. Okay, 2D, 3D. Okay, nonlinear, you have tree and graph, mainly these two categories. Okay, tree and graph. So a tree is actually cyclic. A cycle is a non-cycle. So tree is like something like this, a cyclic data structure. And graph is circle, so you actually go to this, something like that. You know, this graph. Okay? So tree and graph, actually the definition is cyclic or non-cyclic. Okay? And then here is the United States map. You can basically represent by a list, right? Which state you have. And you can also use the border for the connectivity and build a graph. You know what I'm saying? So that actually data representation have many. You can do a long list for different state, or you can do California, Nevada, and then it bordering Arizona, bordering Oregon. That's a different, that's graph. So there is no fixed way of representing data. It's up to you to make arrangements. So what are the abstract data types? Remember the goal of the software development: robustness, adaptability, reusability, and robustness. Okay. These are different things that you need to look at. We want it to be able to reuse. So actually for module or abstraction, we talk about abstraction, right? Last week we talked about abstraction. So the abstraction, you have a class or module or class or structure. It all help the reusability, right? Adaptability is actually you can scale, move up or move down, make it bigger or smaller, or sometimes it's like generic computation. You can put integer there, and you can also put double there, right? Those are generic programming, or using the template in C++. Okay, and robust is like you need to try to support as much function as possible. That's ADT, abstract data type. Okay, so the data type we talk about is the integer, real, character, Boolean, and ADT is those are stack, queue, stuff. That's abstract one. So stack and queue are abstract one. Okay, let's keep moving, and then they are simple ADT and the complex ADT. So how can we choose a right data structure? Two things you need to talk about to look at the data structure. One is interface. Interface means, is that easy to use or not? Okay. Second one is efficiency.
So right now the stuff you're teaching me is like stuff that I should recognize when I'm doing code, right?
Yeah. For example, if I ask you whether you use the array list or array, right?
And I have to think about like whether or not it's easier for me to use and whether or not it saves, is it like efficient and stuff?
So if you wanted to do insertion, which one's better? Many insertion, which one's better?
Array list?
Array list, yes. Array list, because you can insert at any location.
Yeah.
Right? And if I just do linear search, which one's better? This one's better.
Array.
Yeah. So that actually is the so-called interface, the how many functions you can get. You know, the operation that's supported. And then efficiency is like, okay, either data structure running fast or slow. Okay, so these two factors, interface, easiness for use and efficiency. So let's look at this. Okay, the designer of Python and many choice make when they implement this data structure. So this actually is quite successful in Python, and also it makes Python very close to Lisp or ML, the ML language. Those are functional programming language. So Python is almost like a functional programming language because of the use of the list. Okay. So these are two common things you do. You actually do indexing and then assign to the index position. So indexing actually is A of this. It is right hand side value or left hand side value.
Come on. Wait, what?
Is that indexing is the right hand side value or left hand side value?
Indexing? That's the left hand.
That's the right hand side value. Assigning to a index value, assigning to the index position, that is left hand side value. Right?
Okay.
So both of the operation actually is a order of one operation, right? Because you look at the edges, you calculate edges and you get it, right? So another common task is to grow a list. So insertion or deletion, actually it has different things. And also it depends on the algorithm used. Say if I have a list and I implement by linked list, How is the insertion time? Order of 1 or order of n? Append is order of 1, right? Concatenation is order of n. Append is like, I have a list, I just put it to the end, right? Append, right? Oh, I mean, let's see. Wait, this is not, concatenation should also be an order of 1. If you do insert, then it's order of n, k, because you need to find out where it is for the list. Right? But if the list is done by array, say it's a array list, then insertion is more costly. So let's look at the complexity now. Actually, I'm not sure what this guy is trying to say right here. It has a table, so let's look at it. Okay, the next one actually is like, I have a test 1, test 2, test 3, right? So each one, I have a list. So every time I put appending a list into the original list, right? So you actually start going from, so the result of this one is append, right? So originally I have empty list, right? And then I append with 0, and next one I append with 0 and 1. Your 1 got appended in, okay? So this one is list, this one is append, and this one is like, I use to arrange to make tuples and then make list, right? So this actually have 4 different way of appending, right? 4 different way of appending. And number 1 is called concatenate, to connect 2 things together. Second one is called append, to list append. The third one is, so concatenate, each time it is 1 by 1 putting into the list, right? Appending is, well, appending should also be 1 by 1. And then the next one is comprehension. And the last one is use range. So forget about the name. I don't think this name make any sense. It's just different way of creating a list, okay? This one is list comprehension. And this one is list by range. This one is list by append. This one is making list by concatenate. Okay, that's the name. Not really list stuff. It's not an operator itself. It's how to make a list. So we have this, right? We have this 4 function, right? And let's import a timer from timeit module. We import a timer from timeit module. So here we have a timer. So here T1 is a timer. What timer? We actually call the test1 function, and we use the import function to get the from main, actually this function, from current function. We import a test1 and then put a test1 over here. Okay, and then this one is like I print the concatenate first, right? And then print out the time, the span when I execute the test1 for 1,000 times. Okay, this number equals 1,000 means I run 1,000 times. So each one I make a 1,000 data list, and I run for 1,000 times for making that list. Okay, so actually 1,000 by 1,000, you get what? 1,000 by 1,000, you get million seconds. Right? So apparently these 3 others are not of n squared. The first one is n squared concatenate, maybe.
Yeah.
You know what I'm saying?
Uh,
I'm sorry, it's just order of n. The single operation is order n, but actually it times 1,000. That's another n. That's this repetition. Okay. So the other 3 actually order of 1 for a single operation, but they all need to time by 1,000, not actually the number for iteration here. So this can run use the timer to. So you must remember this different to use the timeit and import timer, and put your function here, and then import the function from main, right? And then this one is named, is not. So this one, they really the calculation of the time by running the function by 1,000 times. This is time it. The timer dot time it. So you set up a timer for a function, and that timer run for 1,000 times. This one, this pair is more important. This pair is more important. Set up a timer, and then get the timing. Okay. So this actually tells us what you can actually measure the time I run through here for 1,000 times. You know, this is like measurement of time. Timing is a module to measurement of time. So previous one, we use the analyze and an analytical model, right? An analytical model only analyze for order of n. But right here, we actually measure real time. And which one is more accurate? In terms of measuring of the how fast it is, which one is more accurate? This one is more accurate. This one is more accurate, right?
Yeah.
But this one actually, this is for real. That order of n is on paper. But this one will solve the problem with the language you choose. The language you choose, right? Solve with the machine that you choose, right?
Yeah, so it's like
solve with other task on the machine.
Things can cause it to change, right?
Yeah. The situation may change. But
n doesn't change.
So. Yeah, but the ratio, if you keep the right ratio, it actually is closer than what it should be, because the order of n is a rough estimation. No, it's not really that exact. So this one is actually a real estimation. And also, sometimes we run something with a benchmark. Okay, so right here is the order of different operation for list in Python. Okay, you have indexing, you have index access, you have append, you have pop, you have insert, you have delete operator, you have iteration, you have contain, you have get slice. You know, this different function is the order or whatever, okay? And I don't think the purpose right here is to remember all the orders, but to actually know how you can measure the time. So basically, you analyze a program, you can use a measurement of time, right? You can do measurement of the operator, use the overloading one, right? You can usually calculate the order of n by the big O notation. Right? These are three different ways of analyzing an algorithm. Is that okay?
Yeah.
So time module. So time module, we discussed it already. It's a way to demonstrate the time difference. So basically, it just, if you remember, right here, it just have a time class, put in your function in there, and then import from the main, right? Set it to a timer, and this timer run that time it, right? For the number equals number of iteration, you run the function from how many times, right? This pair actually, one set up the timer, the other one run the timer to estimate the function, how many times the function run, how much time the function is used, okay? So basically right here, again, you have a pop and you make two lists, X list, right? You make one list, and then you actually set up a timer for X pop and then import the X, right? And then you actually time it, okay? You time it, you actually have the pop 0 and time it by 1,000 times, something like that. Okay, more then next one's pop 0 and pop empty. Already get it. This one similar to that one. Okay, this one actually, this team 4 actually is running a 2 million list entry for 1,000 times. Okay, and the next one actually is set up two timers, the same two timers, but actually run run what? We have 3 entry, and actually it perform differently. Actually, this range is for what? I is for the list size. It use a different list size. Okay, it actually use a different list size. Okay, it actually use a different list size, right? It changed the list size for different list size. The previous one don't change the list size. Let's look at the program. Okay, Let's look at the program.
How much is left?
I think we are close.
Okay.
And let me check it. Okay. Why? You have something you need to run?
No, I'm just tired.
We are at the list, right? List almost done, and we have dictionary and then summary.
Okay.
We are actually this 5 here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 pages. Okay. So we have 11 pages left. So let's have list 4. So list 4 is that timer one. Okay. And just run a 2 million sample, 2 million sample. So let's run it. 2 million sample of pub 1 or pub 2. Pub 1 or pub 0. Pub 0 or pub. Well, what's the pub 0 and what's the pub? You remember that? Why
pop
is it?
Is like you pop the thing out of the thing. So
yeah. And how about pub 0?
I'm not sure about pop 0. Pop 0, is it the pop the first one?
Yeah, pub 0 pop the first one. So actually, pub 0 is popping this one. Pub is pub this one. So why pub 0 is actually taking more time? Because if you delete this one, maybe you need to shift. This is actually like an array well, this in Python actually is an array list in Java, and actually array list is an array. Use array to implement list. That's called array list. Is that okay? And then this in Python still be a array list. Okay, even though the name's list, but implementation is array list. So pub 0 is actually pub ahead. It takes longer time. Pub n is just jump the last one. It's actually way easier because you don't have the shift. Is that okay? So that's number 4. Listing number 4. Listing number 5. Changing the length of the list. So basically, if you have a longer list, it will take longer time, right? But the pub 0, pub end probably no change. You know, is always the last one. So let's run and see how it works. Okay. So let's do this listing file. So you can see like pub is almost no changing, right? Well, this actually has minor change, but actually it's probably because of the runtime issue, right? But pub 0 actually keep growing. You see that? You see pub 0 actually keep growing, right? So apparently this one, the first one, pub 0 is a constant time. And then pub 1 probably is pub 0 probably, pub is a constant time, and pub 0 probably is a linear time, order of n algorithm, something like that. Okay, let's stop it. Okay, so that actually is something you can study. Okay, so you can see that using the timer actually is quite useful. And different languages have different timer. Okay, different languages have different timer. In Java is the java.util or current time milliseconds, right? You remember that one? Getting the current time milliseconds, and then use that to minus the other one. So at the beginning of a program, you have this one is, I'm sorry, this one will finish. This one finish is 5. Okay. So in Java, we actually had you can do like long equals star, long actually star equals current system that current time in minutes. You remember that one? Okay, that's actually star, and then you have the long end equal system that current time minute, and in between you put a program, and then you subtract the star and end, you should get the time in between for Java. Same thing for C++. So right here you actually have a pub 0 and the pub. Okay, so as you can see, you will make a chart. As you can see, pop actually is a constant time like this, and pop 0 actually is something like a linear growth. Okay, is that okay?
Mm-hmm.
So that's actually the pop and pop 0. So dictionary. The second major dictionary data structure for Python is dictionary. And dictionary differ from list, right? And that the most important thing is that now get the item and the set dictionary is order of 1, okay, because there may be a hashing table. So important to know that set operation can be order of n. Let's look at it. So copy is order of n, get item is order of 1, set item is order of 1. And dictionary may have hashing table. Dictionary may have hashing table. So you have like dictionary, say Eric, right?
Mm-hmm.
And this string actually may go through a hashing function and go to a location directly. So get object, set object, actually maybe just order of 1 is a constant time. But copy, you need to copy 1 by 1, 1 by 1, 1 by 1. So actually order of n, right? Content is order of n. Iteration, you need to be order of n. Content is order of 1 to check whether it's in there or not. You just need to check whether the variable can hash to some location or not. Okay, so efficiency of the dictionary. Our last performance experiment compare performance experiment. We will compare the performance of the content operation for list and dictionary. So now you will compare dictionary and list. In the process, we will confirm that content operator is in list order of n, but in dictionary it's actually faster.
Mm-hmm.
So as you can see that actually dictionary maybe is a better algorithm, but is that free or no? Is that faster and is free or no? I would say no.
No.
No, it is not free. Actually, you need to build some extra hashing table, so more memory involved. You know what I'm saying?
Mm-hmm.
It may be more memory involved, and then this is only an array. So here maybe okay. We know dictionary is more complicated than this, right? But how comes that the content operation dictionary can be faster? That means that you have something hidden that you don't know, right? So the experiment we are used to compare to are simple. We will make a list, a range of number in there, and then we pick up a number at the random pick, okay? And then we will repeat the same experiment for dictionary that contain number as key, right? So that's to compare to data structures efficiency. So basically just keep the number as dictionary and then the list. So we have this list, and then we use the number and none is the value. So we just make a dictionary with the key that is the same as the list data. And then we use the timer for 1,000 times, run 1,000 times. Okay, to do last name and D time. And T is actually doing this function, checking whether a random number is in the set or not. So basically, you measure this function and then do 1,000 times for it. Okay, so this is this time, this dictionary time, and then compare the two. Okay, so let's go to list number 6. This team number 6. So basically, right here, you try to create a list and dictionary of different size. Okay, and then the function to check is random access of a certain location, right? And then the list actually is a data of certain size, and then dictionary is also of the same size, but none as the value data field. So key is the same as the list. So let's run this one. So as you can see, the first one is I, right? The data set size. The second one is list time. So you can see the dictionary time is always faster than list. So actually dictionary is even a better data structure than list to do. This gives you the flexibility of programming, but dictionary actually is a better performer. Is that okay?
Mm-hmm.
Okay, so that's the comparison for list and dictionary in Python. So here give you some example of how to compare the different dictionary data structure. So that's this sheet. That's actually this file. Let me see. So that's dictionary, and then we see this, and then that's the simulation time by from the book. Okay, this one is from the book, and then that's the last one. Comparison of dictionary. So dictionary just order one, so it actually lie flat, right? This is like a linear operation. So and who can help you to do this plot? PyLab can give you this different plot. So this is somewhere you should pick up your PyLabs, because when you do the operation in CC++, you may need to do a lot of this plotting. Okay. So do learn PyLab. I will teach you that if you don't know it. Okay. Give you some idea of how to do plotting in Python. Summary is easy. Algorithm analysis is the implementation, independent way of measuring the algorithm. So it's a big O notation. Okay, so it should be big O notation just on paper, but real program you will do measurement to estimate it. And in learning data structure right now, and I would actually suggest to use the real programming language to learn it. And I suggest this Python is a very good pseudocode or language to use for analysis of the algorithm and data structure. Okay, and this chapter 2 just give us the overview of how to study algorithm, and then from chapter 3, 4, 5, you start to look at different data structure and algorithm. Is that okay? Okay, so bye now.
Okay.